Hey folks, good evening. This is Mr. Murray coming to you with a little video on the composition of functions. Okay, this is a concept that we talked about briefly, but which actually fits in pretty well to the unit that we're currently on, which is all about starting to make connections between polynomial and radical functions and how they fit together. All right, and when we go into talking about inverses, we're going to see the role that composition plays in terms of showing us how inverses are connected. This is a pretty higher level skill, and it's not obvious how it works. It seemed like people are starting to get it a little bit, but I thought I would go back in and do another explanation, okay? So when we think about a function, right, we could think about a function as like a machine, all right? And we got something that goes into the machine. Let's call this machine F, all right? And so we've got a number, and it's rolling in through this conveyor belt, okay? And it goes into the machine, all right? And out pops, this is my in, and out comes a number, okay? That's a function. And when I put in one number, I expect one number to come out. The biggest thing is that every input has exactly one output, right? And we can make all different kinds of functions, right? We've learned so far last year in course 1, right? We learned about linear functions. We learned about quadratic functions, exponential functions, piecewise functions, absolute value, all kinds of functions. But what if I told you that I could string these machines together such that the output for F is immediately fed in to G as an input? This is called the composition, and that's what it looks like when the output of one function acts as the input to another function. Okay, we write this in two ways. One way we write it is G of f of x, or whatever letter you decide to use for your input. It could be an A, it could be a B, it could be a W. Okay, and this means to take the formula for f, or the functions for f, the outputs, and plug them directly into G. Another way you sometimes see this written is G of f of x. Okay, it can be written a couple different ways. These more or less are interchangeable with each other, right? G of f of x, right? And someone pointed out today the O might even stand for of. That's like the first time I ever heard that, but it's actually pretty good intuition there, okay? So let me give you a little example. Let's say that f of x, okay, let's call this a linear function, 2x minus 5, okay? And I'm going to call g of x, let's call it, I don't know, how about we call it a quadratic? How about a cubic? 3x cubed minus 2, okay? So what I'm going to do is, let's say that I want to know what is g of f of 2, okay? What I'm asking you to do is, I'm asking you, well, look, I can't figure out what g of f of 2 is, because what information am I missing, right? I don't know what f of 2 is. So what I need to do is I need to start in the middle and work my way out, and that begins by figuring out, well, what is f of 2? Okay, so I know that f of 2 is equal to 2 times 2 minus 5, okay? And that's 4 minus 5, which is negative 1. And so what this is essentially equivalent to is that since f of 2 equals negative 1, okay, I'm asking you really to be plugging in negative 1 to g. And when we do that, what we get is g of f of 2, which is equal to g of negative 1, which is equal to 3 times negative 1 cubed minus 2. And negative 1 cubed is negative 1. And when you multiply by 3, you get negative 3 minus 2 is negative 5. Okay? So therefore, g of f of 2 is equal to negative 5. Okay? So what did I do there? Well, what I did is I plugged the number 2 into f. Out came -1, and then I took that output from f and immediately used it as an input to g, right? So it's a little composition of functions. Okay, and that's how composition of functions more or less works. You're using the output from one as the input of another. Okay, I'm now going to ask you to try a couple problems. Now, one student asked me today, are you just going to give me g of f of something without giving me any more specifics? Let me just tell you one thing just to put your mind at ease maybe. In order to do composition, I have to tell you what the functions are. I can't ask you to plug into f unless I give you like a graph or maybe a table or a formula where it's actually doable. If I just say, what is g of f of 2? And I don't give you a graph, I don't give you a formula, I don't give you a table for reference, there's no way you can solve that problem. Okay, so let's take a look. Let's say that f of x is equal to, let's call this a quadratic, x squared plus 4. Okay, let's call g of x -1/2 x plus 6. And I'm just kind of making these up as I go. Okay, and then let's call h of x, why don't we just call it a simple x cubed minus 1. But we stick with that. Okay, so here's what I'm going to ask you to do. All right, I'm going to ask you to figure out a couple things. One, all right, what is g of f of 0? Okay, how about what is h of f of 2? Okay, what about f of h of 2? See how those are different? And lastly, I'm going to ask you, what is, ready, this is a tough one, g of f of h, okay, this is not an easy one, of 3. How about we make it, I'm going to make it a 2. Keep my numbers a little bit smaller. 1, 2, 3. Okay, so here's what I want you to do. Given the function f of x equals x squared plus 4, g of x equals -1/2 x plus 6, and h of x equals x cubed minus 1, I want to know g of f of 0, h of f of 2, f of h of 2, and g of f of h of 2. Okay, so take a second, pause the video, attempt to solve these, and when you're ready to see me work through the answers, go ahead and unpause the video. All right, I'm going to work through these one at a time, okay? So let's start with g of f of 0. The first thing I need to do is I need to figure out, well, what is f of 0, right? You can't get g of f of 0 until you figured out what's f of 0, right? So f of 0 is equal to 0 squared plus 4, right? And so 0 squared is 0, and 0 plus 4 is 4. So what I'm actually asking you to determine for me is g of 4, because that is what f of 0 is. It's 4. So what is g of 4? Well, we'll come on over here, and g of 4 is equal to -1/2 times 4 plus 6. And -1/2 times 4 is -2. And -2 plus 6 equals 4. Go figure. We actually end up getting, pretty interesting, right, the exact same output. Now, that's just a coincidence. It's not always going to work out that way. That just happens to be because of the rules that we used, okay? Well, now let's move on to h of f of 2, okay? So h of f of 2, okay, we want to plug in 2 for f. We have to start inside and work our way out. So I've got 2 squared plus 4, which is 4 plus 4 which is 8. So what I'm looking for is h of 8. Now for this one you might need a calculator. That's not an easy one, so I'll do a little bit of arithmetic over here, okay? So what I've got is I've got 8 squared, that's 64, and I'll just do 64 times 8 real quick. So that's 32, that's 48, 512, okay? So h of f of 2 is the same thing as h of 8, which is 500, which is, I guess we should do, let's plug it one at a time. 8 cubed minus 1, which is 512 minus 1, which is 511. Okay. Lastly, let me just kind of box this off here. Lastly, let's do f of h of 2. So let's start from the inside, right? I'm on the outside. I'm looking in. All right, that's my little musical interlude for this video. So 2, 4, 8, right? We're gonna do right h of 2. That's where I'm getting that from. So 2 cubed is 8. Minus 1 is 7. And now I'm going to take 7 and I'm going to plug it in to what function? F. So I'm looking for f of 7, which is 7 squared plus 4, which is 49 plus 4, which is 53. Okay? Lastly, let's look up g of f of h of 2. Well, ordinarily, you'd start by plugging in, you'd start by getting h of 2. We know that. That's 7. You take that, right? And you'd plug it into f. And we've already done that. That's 53. So our last step is to plug that into g. And we plug it into g. We get half of 53, negative a half of 53 plus 6. All right, and there's a lot of ways you could do this. I'd look at 53, well, that would be 26.5, right? So we could do the math, right? So, right, well, 2 goes into 5. Well, first of all, it's a negative twice, remainder of 1. Okay, we get 13. 2 goes into 13 6 times. The remainder of 1 out of 2. And what we end up with is negative 20.5. You could have done this in a few ways. If you wanted this to be negative 53 over 2, you could have looked at it as 41 halves, which is negative 41 halves. Lots of different ways you can do it. Again, as long as you do it in a mathematically correct way that yields a correct answer, and it's equivalent to the answer that I got, I'm not looking to judge you. I'm not looking to say, hey, she didn't say negative 20 and a half because this guy said negative 20.5 and this guy said, negative 41 halves. It's not about that. I care more that you can go through here step by step than that you have the correct way, a decimal versus a mixed number versus an improper fraction. Okay, so again, if you struggle with this, you try, please go back and take a look at it and make sure you understand where I'm coming from. And then in a minute, I'm going to go on to a little bit more of a sophisticated problem. All right, I'm going to move on and I'm going to go and show you 1 or 2 more things here, okay? Because we got some good time going right now. So I'm going to show you another important thing. And that's that composition can actually be used to plug formulas into other functions. Let me give you an example. So let's let f of x equal x plus, 5. And let's let h of, we'll call it h of x, I guess. H of x equal, x minus 5. And let's let, k of x equal x squared plus 2. Okay, so what if I wanted to know, well, what is f of h of x? So now what I'm going to do is I'm going to take the entire function of h of x and plug it into x. Okay, and here's what it looks like. So here's my x. So let me show you what it looks like to drop it in, right? I'll put my parentheses here. And let's drop in h. Okay? So this is what it looks like when we drop in h into f. And notice one really cool thing that happens is the 5's will cancel, and all that I'm left with is x. Okay? And I wonder what happens if we do that the other way around. It's h of f of x. Well, h of f of x is, well, let's set up our formula. So let me drop in. Okay, here's h of x. And I'm going to go ahead and I'm going to plug in f. And notice what happens. Boom, boom. Okay? All I'm left with is an x. So what does this mean? What this means is that f and h are inverses of one another, okay? And if you think about it, that actually kind of makes sense, right? Because what is the opposite of adding 5 to something? Well, it's subtracting 5, right? If I start with, I don't know, 23, and I add 5 to it, what comes out? Well, 28 does. But what if I start with 28 and I subtract 5? Well, 23 comes out, right? So by doing this function and then undoing it, I'm right back where I started, okay? And this is going to become a fundamental test of whether a function is an inverse of another function. And I probably will talk about that in class as well as in a subsequent video. So for example, we know these are not inverses of one another. So let me show you an example. I'm now going to do k of h of x. So what this means, okay, is I'm going to take h and I'm going to plug it into k. Okay, so I'm going to get x minus 5 squared plus 2. All right, let's do this out. So I want to square x minus 5. I'll make a box. You can do it with the FOIL method if you want. But I love this because this method actually works for all kinds of things. So I get x squared minus 5x minus another 5x plus 25. So what does that give me? Well, it gives me x squared minus 10x plus 25 plus 2, which is equal to x squared minus 10x plus 27. And actually last year, at least folks who had me, and I'm pretty sure the other math teachers last year did this as well, this was just kind of like converting from, remember this is vertex form into standard form, okay? And we can see that these functions are not inverses of one another because when you plug one into the other, it doesn't completely undo it. You're not just left with x anymore, you're left with a whole bunch of other stuff. And what's actually really cool about this is you can use this to explore properties. Let me give you an example, one last example. And I'm going to do a u-try after. So let's say I plug in k of negative x. What does that mean? Well, let's think about it. What that means, okay, is that wherever I see an x, what I'm going to do is I'm going to plug in negative x. Okay? And now notice, what's negative x times negative x? Well, over here I'll explain to you, right? Well, we know that negative x is equal to negative 1 times x. And so if I square that, I'm squaring negative 1 times x. So what I'm really squaring is negative 1 like that, right? And so negative 1 squared, well, that becomes 1. X squared becomes x squared. So this is really just the same as x squared. So look at this. This is actually really cool. That k of negative x is actually the same thing as k of x in general. And what that actually means is that this is what we call an even function, okay? Because an even function means if you plug in a number and then you plug in its opposite, you're always going to get the same output. And that we know is actually true a lot of times about parabolas, especially ones that have a vertex of x equals 0, okay? Because, or rather, I guess I should technically say an axis of symmetry of x equals 0, but what I'm getting at is when the x of the vertex is 0 and it's nice and laid along the y-axis, right, with the y-axis being the axis of symmetry, you get a really nice symmetrical function like this, right? And if we want to use the Mitchell trick, right, this is what x squared plus 2 looks like. 1, 2, 3, 4, 5, 6, 7, 8. So we have this, we got 1, we've got 1, 2, 1, 2, 3. Okay, we got the 1, 3, 5 trick. I think HB took credit for this too, the Mitchell HB trick. Okay, notice that beautiful symmetry, that beautiful evenness that we see. Okay, so go back, and if you need to take a second to understand any of this conceptually, I really encourage you to do that. Otherwise, in 1 second, I'm going to move on to just a couple of examples. All right, so forgive the sound of ripping paper there, but I thought I would save the environment. And I'm going to give you a couple of quick examples of plugging in formulas, okay? So let's let f of x equal, I don't know, x squared plus 6, okay? And then I'm going to let g of x equal the square root, and we haven't really talked about square root functions, but we could plug into them. I'm going to let it be the square root of, let's see, x minus 6. Okay? And then I'm going to let h of x be 3x plus, I don't know, 15. All right? Here's what I'm going to ask you to do. I want you to find a couple things. I want you to find f of g of x. Okay? Let me just zoom out a little bit just to make sure we can see everything. I want you to find g of f of x. And then I want you to find, let's see, h of f of x. And then I want you to find f of h of x. Okay? So take a second, pause the video. Let me just zoom this out a little bit so we can see everything. So folks, take a second, okay? Digest this, pause the video, try to give me those nice compositions, and then when you're ready, we'll come back and I'll show you the answers to these 4 composition problems that you see here. All right, let's take a look. So I've got f of g of x. So what gets plugged into what? The g's in the middle. So I'm taking the g and I'm plugging it in to the h. Okay, so the g, or rather the g is going to go into the f. So let's take a look. So let's drop it in. And folks, if you want to on a test use multiple colors, I really encourage you to do that, okay? That's totally allowed. Okay, so here's what I've got. Now, we're squaring a square root, and we now know what happens when you square a square root is the square root is peeled off. Like, remember, we talked about square root of 2 times square root of 2 is square root of 4, which is 2. Square root of 9 times square root of 9 is square root of 81, which is 9. So whenever you have a square and a square root, those things are actually going to undo each other, and what you end up with, lo and behold, is x. What if we do it the other way around? What if we plug f into g? Let's take a look. So now what I'm going to do is I'm going to do x squared plus 6 minus 6 inside my little house here. Okay? And notice what happens. Well, first of all, when I can just go ahead and peel off those parentheses, right? There's not being multiplied by anything. Those go away. and I get the square root of x squared. And the square root of x squared, well, that's just equal to x squared to the 1/2, if we think about it with rational exponents, and then the 2 and the 1/2 cancel out, and I get x. Wow, so those things are inverses of one another, okay? And remember, like I said, in a subsequent video, I will show you not only how to calculate the inverses, like where did that even come from, but also how to prove them. Okay, h of f of x. H of f of x means we're taking what and we're plugging it into what? We plug in f into h, okay? So here I go. Okay, x squared plus 6 plus 15. I do my wave check. Okay, and someone suggested try to make it look like a do-rag. I'm not quite artistic enough to make it look like a do-rag. Okay. Now I combine my like terms. The 3x squared, that's not going to combine with anything. The 18 and the 15, it's going to become 28 plus 5, which is 33. Okay, a little formula there. And lastly, f of h of x. This one's actually harder. So here, what I'm doing is I'm going to do, sorry about that. Okay, that's a little bit harder to square, but when we square it, I get 9x squared. Okay, and I should get 90x, and that's because you do 15 times 3x, that's 45x, like when you actually do it out. So it helps you, I'll show you what the square is there, right? There's the 9x squared, there's 45x, here's another 45x, okay? And then I have to do the 225, because that's the 15 squared. Then I add my 6, and I get 9x squared plus 90x plus 231, okay? So folks, composition is a really, really important topic. We use it, one, to get a kind of deeper depth into how these functions work and how they come together and combine. And as I've shown you now, it's going to become a crucial test of when functions are inverses of one another, right? We now have a sense that if I can plug in one function's formula into the other and get x, and the same thing works vice versa, then what that means is that when I plug in a number into one function and then plug it into the other, I'm back where I started at the original number. And what that means is that those functions are inverse of one another. Because what they do is they undo, the inverse undoes the effect or effects of the original function, okay? And again, this is becoming a really, really big moment because, and I'm proud to be doing this with you, this is a moment where we start to really fit things together, right? We start to really fit our investigation of polynomials together with our investigation of roots by taking it a step further and looking at how the ideas and how the functions are connected to one another, okay? So I hope you found this video to be informational. Again, I really encourage you to take a look at hopefully some of the timestamps that are in the description, all right, and to really get a sense of what's going on here because this is a really important concept, okay? So just really, guys, stay positive, believe in yourself, and remember, as I always say, you can do it, all right? So, folks, thank you for watching. Keep the questions coming. Don't forget to subscribe so you can see my future videos as they come up. And remember, you can do it. All right? Have a wonderful night.